Talked about recursion last class, right? Remind me, what is recursion?
Referencing the loop.
Okay, you really like that loop. You like that word loop.
Definition.
Yeah. So yeah, 'cause you wanna throw the word loop into pretty much every answer, don't you? Yeah. Like the return statement, it ends the loop. Okay, return ends the function, right?
Yes.
Okay, yeah. So what's a recursive call? A recursive call is that's when a function is defined in terms of itself, or maybe even more specifically, when a function calls itself from within itself. All right. So we looked at factorial last time, and we wrote a iterative version of factorial as well as a recursive version of factorial. Oh, and so here, nice trivia for you. When I say iterative, I'm talking about loops. So you should be a big fan of iterative. You should be a big fan of that guy. Now, so we wrote an iterative version of factorial. So 5 factorial would be 5 times 4 times 3 times 2 times 1, just looping through, counting down. And then we wrote a recursive version of factorial, where 5 factorial is 5 times 4 factorial. 4 factorial is 4 times 3 factorial, so on and so forth. Okay? Now, is recursion better? Is a recursive solution better than an iterative solution? Why? Okay, so recursion is less memory efficient? Why? Why is it less memory efficient? I agree with your statement. Now support it.
So from what I remember on Friday.
I can already see in the future. He's going to be one of these guys on TV that's announcing these sporting events, kind of, talking about the team he likes the best and why it wasn't a foul. You just seem like a sports commentator. You have that personality.
Appreciate that.
Yeah, I like it personally.
You say you had to keep track of more variables or something?
Yeah, computer science skills are a bit sketch.
Yeah, a little bit.
Most sports commentators don't
Don't have computer science. All right, so you keep track of more variables, you mentioned, right? More memory. Okay, so every single time we have to pause a function. So when we're working on 5 factorial, and we have to say, okay, well, I can't give you the answer to 5 factorial until I've calculated the answer for 4 factorial. So I got to put this guy on hold, which means holding all those variables, holding the current state of that call, that function. And I'm going to put this guy on hold right here. And then I'm going to go and calculate 4 factorial, which is the exact same lines of logic, but instead of your variable being passed in being equal to 5, now it's being equal to 4, and any other stuff that's going on in there, right? Okay, and then we're going to put that guy on hold. So now we have 4 or 5 or however many times we're going through here, copies of this function all put on hold, and that equals storing a lot of variables and other stuff. Whatever it takes to kind of pause a call through a function is not efficient in terms of memory. Okay, good. So what's good about recursion then? Go ahead.
Well, it's a bit more elegant code, easier to read, potentially easier to debug, and on a larger scale could also shrink the total file size by a significant amount.
Right, at the cost of then using more memory.
Right.
Okay, and easier to read. I can't necessarily fight that argument. It would probably be easier to read, or potentially easier to read, for somebody who does understand recursion. Yeah, otherwise, typically, and I think I mentioned this to last class, you as a group are not going to like recursion initially. It is a hard thing to kind of wrap your mind around. When you take it to the programming world, we deal with it all the time in real life. We think about things in terms of other things all the time, right? But since we don't attach it to a scary sounding vocabulary word, and we're not having to translate stuff for the computer, there's less of those extra steps. It's something we've been all working on for 20 years, right? We've all been practicing being people for 20 years, as we're pretty comfortable with that. Okay, we've been practicing being computer programmers for 10 weeks, right? And the first 4 of those weeks, we weren't really talking about programming stuff. So we're noobs, right? This isn't something we're good at yet, and that's okay. That's okay, because I mean, if you think back, a lot of us don't have the memory of this, but when you think back when you were a baby, you weren't as good at being a person as you are today, right? You were falling over all the time. At first, you couldn't even stand up. You were just sitting there, couldn't even hold your head up. I mean, you were useless, right? So, put that into context as you're kind of measuring your computer science skills. So, I mean, I'm really saying there's still hope for you. I mean, you're not set for a sports commentator career.
You also called it Noobs.
Huh?
But you also called it Noobs.
As babies, yeah. Well, mostly
then you
still.
compare
I
it.
could bench press 350 now, baby. How much documentation?
You couldn't bench press 350 now. I mean, there's a slim chance I'm right. I'm wrong, but I can't. I mean, I'm thinking 200 max.
What are you thinking? You don't think I'm huge, Doug?
I can't bench press 350, and I'm 3 times your size. I don't even know what I might not. You probably could bench press more than me. That's not even a size thing. I mean, it's not 350. You know, it's although you saw like there was some kid a couple years ago, like a 10-year-old or something like that had like some weird disease that their muscles were like overdeveloped.
Yeah. He's like hanging on poles, like sideways.
Yeah. I always thought that would be cool, being a big guy. To like, one thing I'm working on, because I'm working on a lot of flexibility stuff. I want to one day be able to come into class and just like slide out into the splits. I can actually get pretty close right now. Yeah. I mean, but I do most of it in the pool because I don't want things to break. Yeah, but wouldn't that be like extra impressive when you see like a big guy? You know, you see some gymnasts getting this now. That's what gymnasts do.
And after that, we set up Mission Impossible laser course for you to go through.
Well, just I get those splits doesn't mean I become smaller in terms of how much space I take up. So we're gonna have to start moving into 4th dimensions in that case if we're gonna be successful in that endeavor. I guess is what I'm saying. All right, so we're not gonna like recursion at first. It's not gonna make a lot of sense to us because it's gonna be hard. If you kind of think about how the semester has gone so far, the second you start thinking you're kind of getting something, then we throw one more thing out in front. Then like, oh, well, that's hard again, right? So we always want to keep you challenged. And eventually you look back and you say, oh, well, all that stuff I used to find hard is now easy. Now I have new stuff that's difficult. Okay? So recursion, memory inefficient, but potentially gives us kind of nice, short, potentially elegant solutions, that kind of stuff. So there's a kind of a trade-off there. Some problems, every now and then we might run into a problem that really lends itself to a recursive solution where writing it iteratively would be difficult. And I did reference something last class that there's kind of an accurate sentence that might not mean tons to us right now. It'll mean more when you get into like the later portion of the next class, 250. But any problem you can solve recursively, you could also solve iteratively with a stack. So we have this data structure thing called a stack. Now, the reality is recursion in programming languages is implemented with a stack. So what you're really saying is you can either use the built-in recursion or you can just invent your own recursion, and solve the problem. So, choose your poison, whatever makes you happy. Okay, but kind of the important thing to come out of this with is recursion doesn't mean better. You shouldn't be spending your time hunting for recursive solutions to problems. Okay? Every now and then, recursion is going to make some sense. But for a lot of problems, you're going to really have to weigh that memory inefficiency thing. And we're going to be looking at merge sort today, and that's going to be one of those problems. Merge sort makes a lot of sense, but there are 2 recursive calls inside of merge sort. And the larger the data set you're going to be sorting, the worse this becomes, right? The more copies of the merge sort function you have to put on hold. That might say, well, yeah, merge sort might be, nice on paper, but it's problematic from the perspective of sorting big, large pieces of data using merge sort. So kind of keep that in mind, because I'm going to ask you, after we've introduced merge sort, why you would ever choose to use it. Okay, now I'm telling you it is faster. Okay, but we already know recursion is memory inefficient. It would follow that 2 recursive calls would be even more memory inefficient, right? And as our data set gets bigger and bigger and bigger and bigger, I'm promising you that merge sort will mean even more recursive calls, 2 times each. This sounds to be dangerous from a memory perspective. So kind of keep that in mind, because we're gonna swing back and we're gonna ask, why would we use merge sort? Why is it good? Okay, and we're gonna be kind of talking about a different type of computing that your mind's probably not going to yet. All right, so let's go back here. Let's talk about merge sort. And we did read about objects over the weekend, right? That's what we did in the book? Okay. So let's talk about merge sort initially. So objects we're kind of teeing up. We're going to kind of start moving into that, but we want to talk about merge sort first. All right, so we're going to kind of put this in words, and then we're going to talk about the algorithm directly. And then we're going to attempt to solve the algorithm for our homework, okay, which you will not like. But actually, the solution, as he pointed out, is typically very short. Okay, so the actual merge sort implementation is, depending on how verbose you get, no longer really than insertion sort was. But inside those lines of code, there's 2 recursive calls. It's a bit scary. All right. So here's how merge sort works. I'm going to kind of throw an overall sentence that kind of gives the premise. Merge sort works on the premise of having multiple partially sorted lists and then merging those lists together. All right. Now, before I kind of talk about the algorithm, let's talk about that partially sorting, or the partially sorted list merging together step. So it's called the merge step in merge sort. So before we get too, ingrained with the details, let's just talk about why this might be helpful. All right. So we're going to go to another slide here. And let's just assume, actually, hold on, I'm going to steal some boxes from a different screen. All right, so we have 2 lists here. Would you all agree, when you look at this list as a person, that that list is already sorted? 3, 4, 5 is already in a good order. And we would agree that this list is also, actually, no, it's not quite sorted. Now it's sorted, right? Okay. This list is also sorted. What we want to do is we have 2 3 lists that are sorted in and of themselves. We want to create a single 6 list, a list that's 6 buckets long, that is sorted based on these. Okay, so we have kind of our landing zone. We have 6 buckets we're trying to fill with numbers. Okay, we know that this list is sorted in and of itself, and that this list is sorted in and of itself. I'm not even going to throw any variables in here right now. We're just going to solve this as people, but we can, maybe start thinking about the variables that might be involved. So I'm going to put these 2 lists in competition, okay? So the beginning of this list, the smallest number in this list is a 3. The smallest number in this list is a 1. Which should come first? A 1. So we're going to deem the 1 to be the winner. So there's our 1. Now, the current smallest list in this list is a 3. Our smallest value in this list is a 3. We've already used the 1, so now our smallest number is a 2. Which should come first, a 2 or a 3? 2. Which should come first, a 3 or a 7? 3. Which should come first, a 4 or a 7? 4. Which should come first, a 5 or a 7? 5. Which should come first? Any legal position. We're out of stuff, right? No more contestants over here. Or a 7. This is the last kid picked for the kickball team. Okay, so nobody or 7. Well, you're better than nothing. So we'll take the 7. Now we've run out of contestants. All the kids have been picked for the kickball team, right? And we happen to have a sorted list. Would you agree that the algorithm we just went through there, don't think about the algorithm it took to get these guys sorted, but given 2 smaller lists that were sorted in and of themselves, was this pretty easy to put them together into a single sorted list, to merge those 2 lists together in a sorted way? It felt less complex than like insertion sort, right? So because our data was kind of pre-formatted, right? We knew we had 2 lists and we knew both of those lists were sorted. By having that knowledge, we can then apply that merging step that guaranteed us to have a final sorted list without doing a whole bunch of extra checking. That makes sense? All right. This isn't necessarily dissimilar to what we've done recently with the binary search. Remind me, what is binary search? To efficiently search stuff with binary search, what does it require? Yeah, that our data be sorted. Okay, that's our phone book search or our dictionary search. You call it whatever you want. I mean, the computer science name is binary search, but you know, maybe some exam at some point might ask you that, but it's much more important you understand what it means than what it's called. Okay, it requires you have sorted data. Otherwise, it wouldn't work, right? If I just gave you a random list of stuff and said do a binary search on this, I mean, you're throwing darts. At the end of the day, it's a random search that doesn't always work. Now you could do that, right? Couldn't you? What would a random search look like? So I give you 50, a deck of 50 cards, right? 52 cards, and I say randomly find the ace of clubs. You can shuffle it out for you. Is this it? Nope. This ain't no.
Now wait, would we be removing from our?
No, you put it back and re-grab.
Okay.
Okay, even if you did remove, I suppose if you did remove, then it doesn't necessarily become worse than a linear search. If you did remove, if you have 52 cards in a row and you just started at bucket 0, bucket 1, bucket 2, bucket 3. And you compared that to, you have 52 cards, not sorted, and you just randomly selected some card out of the deck and said, is this what I'm looking for? No. You toss it out, now you have 51 cards left. Effectively, that becomes a linear search with a little bit of, I guess, flair, right? Because you're randomly selecting the cards, so it's kind of excitement, you know. But if you always put it back into the list, that wouldn't be efficient, correct? But given enough random guesses, would it eventually work? Oh, sure. I mean, you just randomly pick some card out of your 52. If you know you're looking for it, you'd eventually find it. It might take thousands and thousands and thousands of checks, just depending on, the luck of the draw, so to speak. Since it's going to take a lot of attempts to get the unique 52 numbers that come out of the guess, right? It might even be even worse if you shuffle in between each one, right? So now I'm going to shuffle the deck and then randomly pick a card. Then I'll put it back and I'll shuffle it again and randomly pick a card. But eventually, this is the type of problem a computer can help us with. It would probably, for us, it would probably feel like it almost works instantaneously if we ran this on a computer and weren't doing printing in between. Printing is very expensive. So even though it maybe had to check millions of times, it might feel like it actually ran pretty fast. And under the hood, it's just making random guesses. Okay? But punchline here is that our binary search requires our data to be prepared for the search, for the way it works. Similarly, the merge step, which is actually the sorting step for merge sort. This is the actual way merge sort sorts, is this merge step. It requires that your data be prepared. Okay? That you have two halves of your list. All right? So remember I mentioned that we have merge sort that gets called twice. We call merge sort in the first half of the list. We call merge sort in the second half of the list. And ultimately, merge sort's going to prepare for us partially sorted lists. This list will be sorted in and of itself eventually because of the merge step. This list will be sorted in and of itself eventually because of the merge step. All right. Now we're performing another merge step that takes these 2 3 lists and turns it into a 6 list, which might be preparation for the next step up, which turns 2 6 lists into a 12 list. That make sense? All right. So the question I might ask then is, if the merge step is the step that actually does the sorting, how can we ever have a partially sorted list without a merge step? The merge step requires the left half to be sorted and the right half to be sorted. It requires that. And I've advertised that the way that merge sort sorts is through the merge step. How can I get a partially sorted list and another partially sorted list without ever doing the merge step? This comes down to this idea of a trivially, I'm not spelling this guy that great. Trivially, is that a word? Yeah, there we go. Sorted list. Can you give me an example of a list that without you doing anything extra to it is guaranteed to be sorted? Could be any list. Huh? Fibonacci sequence. Okay, yeah, I mean, go way simpler than this. Huh? Okay, so you want just a list of numbers? How do you know those are sorted by definition? How do you guarantee they're sorted? They got to be trivially sorted. We can't do anything special to it. You just, poof, there's a list in front of me and it's sorted. Trust me. I want you to be able to hand me a list and for me to not even have to look at that list and tell you that it's sorted. What would the characteristics of that list need to be for a list to definitely be sorted without even looking at it? How much work do you have to do to sort a list of one element? Is any list that contains only one thing by definition sorted? Yeah, that's sorted. So a trivially sorted list is a one list. So with merge sort, we can keep dividing stuff up until we finally get a list of one and a list of one. And when we have 2 one lists, we can say, I don't need to merge these to make sure they're sorted. They are sorted because they're one lists. Now we'll bump back up and we'll have a one list and a one list, and we'll merge those together to give us a partially sorted 2 list. So I have a 2 list and a 2 list. Now I'll merge those together to give me a partially sorted 4 list, so on and so forth. That make sense? Remember last time we mentioned this idea of divide and conquer? So we're going to keep dividing our list up. I only have so many fingers, so we can't. That would be a really cool trick, too. Then you start, aliens are among us and stuff like that. Okay, so you start dividing your list up. You just keep dividing it until we finally hit a point where we have a 1 list and another 1 list, and then we can merge those together to give us a 2 list, and we can merge those together to give us a 4 list, so on and so forth. That makes sense? So what I'm going to do here, just to show how this algorithm works, you're going to want to pay attention and make notes of this because you're going to be implementing this for your homework assignment. So I'm gonna scramble these guys up. We're gonna shuffle our list. So we'll do a 7, a 1, 5. Good enough. All right. So we call merge sort. Now, right now, we are, and so let me connect another dot for us before we go any further. Remember a couple of classes ago, we were talking about pass by reference versus pass by value? What's the difference? Remind me. What does it mean for something to be passed by reference or passed by address? Those are synonyms. What does that mean?
That's a copy.
You're always opposite the actual. So make the other guess.
Pass the actual.
Okay, we're passing the address where the guy lives in memory. Okay, so when we pass something by reference or we pass something by address, I'm saying the same thing there. Passing by reference, passing by address, those are synonymous with each other. That means that I'm not giving you a copy of it. Instead, I'm telling you where you can find it in memory. I'm passing you a pointer, which means that any changes you make will have side effect. Okay? Pass by reference is the I tell you where I live, you spray paint my garage, I find out about it when I get home. It's that example. Make sense? Okay. Pass by value is when I give somebody a copy of something and any changes they make to the copy has no impact on the original. Okay? Now we saw that lists and dictionaries are passed how? If I pass a list to a function and I make a change to that list, what happens to that list outside of that function? It also changes. Okay, so lists are passed by reference or by address or by pointer. They're passed in such a way that changes have a side effect. Even if you don't know what they're called, what it's called, if you pass a list to a function and you change that list, it will have a side effect. It will. Everybody else will notice. Anybody else who knows about that list will notice that change. Okay? So in this case, if I'm passing this list around to functions, I'm passing it a reference to that list, which means if I make changes in that list, if I swap this 1 and that 7, that change is permanent and everybody else will notice. Make sense? Okay. So that means that I'm really doing merge sort within the original list. And I'm replacing stuff around and things like that. So I'm going to keep track of the begin and ending of this list. All right, so initially, my initial call to merge sort, my first call to merge sort, is going to have a begin is 0 and an end is 0, 1, 2, 3, 4, 5, right? End is 5. This will help keep it as short as possible, okay? Now, this is my original call to merge sort. So we make an initial call to merge sort. We haven't made a recursive call yet because this is, you got to start the ball rolling somehow, right? So I'm going to say merge sort this list. The first thing we ask is this list trivially sorted? How do you know? More than one value. You got one right. Perfect. Okay. More than one value. This is not a one list. Therefore, we cannot just say it's trivially sorted. Now, it may have been, right? It may have been sorted. The moons may have aligned, and we may have actually had sorted data passed to us. But without doing some checking, as a human being, we can glance at a list and kind of say, oh yeah, that's in order. But to say trivially sorted, if I wanted you to prove that a list was sorted in a programming language, that would actually be kind of difficult, right? You'd have to kind of spin through and make sure each number was greater than or equal to the number before it, and all sorts of stuff like that. It would take logic to do that, right? So we're taking all that out. We're just saying we only care about trivially sorted lists, and because this list, that is because end and begin are different values. That means we have more than one value in our list. Therefore, it is not trivially sorted. Okay? When a list is not trivially sorted, what we do is we call merge sort in the left half, We call merge sort on the right half. So now my call to merge sort on the right half will not actually occur until the merge sort on the left half has finished. And merge sort on the left half is going to call merge sort multiple times as well. So you're going to see this. So what I'm going to do is we're going to make our initial merge sort, our first recursive call will be to merge sort on the left half of our list. Okay, and this is where I'm passing the same pointer to our list, but now begin as 0 and end as 2. So I'm only focused in on this portion of the list. Okay, is this a trivially sorted list? Nope. So I'm going to call merge sort on the left half and then the right half, and depending on how you do your math to divide your list in half, the left half might be the 1 list, the right half might be the 2 list, or the left half might be the 2 list and the right half might be the 1 list. Doesn't matter how you divide your list in half as long as you always do it the same way. Okay, so we'll say 2 plus 0, so end plus begin divided by 2 to give us our middle. Pretty similar to what we did for binary search. So 2 plus 0 is 2, divided by 2 is 1. So that means we're going to have, that's going to be our middle point. And we can decide that middle is going to be the end of the left half. So we'll go ahead and call this guy again. So that means the left half will be our 2 list. So we're going 0 to 1. Is that a 1 list? Nope. Split it, right? So 1 plus 0 is 1 divided by 2 is 0. So the left half will be 0 to 0. Is that a 1 list? Yes, we're done. That call to merge sort finished. Trivially sorted. Then we'll call our second call to merge sort for this guy. Is that a 1 list? Yes. So that guy finished, and that guy would have been middle plus 1, which was 1 to end. So 1 to 1. That makes sense? Let's just for this one time, let's just go ahead and just draw that out. So I made a call to merge sort that looked like this, where begin and end were both 0. And I immediately said, I'm done. Okay, so I did need to take up some memory here in order to make this call. But because I noticed that begin and end were the same value, I know I have a 1 list. I know it's already sorted. I don't have to do anything in this call to merge sort. So that's done. Then I make the second call to merge sort at that level. This is from 1 to 1. It's a 1 list. It's sorted, right? So this guy is done. Now notice, we currently have 3 different calls to merge sort that are sitting here on hold, right? So far we've made 5 calls to merge sort. 2 of them have ended because they were trivially sorted. So now I'm down to 3 calls to merge sort that are currently on the stack, being memory inefficient. Okay? So now I'm on this guy. He has finished his first call to merge sort. He's also finished his second call to merge sort, which means that I have 2 partially sorted lists. This list is sorted in and of itself. This list is sorted in and of itself. I will do the merge step that we saw a few minutes ago. And we'll ultimately have 1 and 7 will come out as the winners, right? Then we'll copy those values back into the positions in our original array from bucket 0 to bucket 1. So this list goes from bucket 0 to 1, which happens to match up with the position in our original array here, 0 to 1. But if you think about over here, when we're dealing with this 2 list down here, this would be dealing with bucket 4 and 5. So I'll be copying bucket 0 into 4, 1 into 5. Okay, because this is the list that we did our merge in. This is a brand new list. Okay, a kind of a fresh list that I use to merge these two partially sorted lists where I just picked winners. So I have this list that's, oh, this is my sorted version. Now you got to copy that sorted version back into the positions in your array that are that you're working with. Okay. So we'll overwrite this with 1 and 7. Now this call to merge sort has been done. He has sorted himself with that merge step, correct? So now this guy ends. Then we make our write call here. Is that a 1 list? Yes, so it trivially ends. We don't do anything special. Now we come back. Now both calls to merge sort here have finished. The first call, oh, I need to update this. Remember, this was passed by address. So throughout history, that list has been updated. The first half of my list is sorted, right? The second half of my list is sorted. I'll do my merge step, so I'll create a 3 list, do the winner thing, so 1, then 5, then 7, copy them back over. So there's my 1, my 5, my 7. And then this call to merge sort has ended. Now I'm able to make my second original call to merge sort. My first call to merge sort just ended. Now I make the second one. So it's going to split this down, do the divide and conquer multiple times. Ultimately, we'll come back and this guy will be 3, 4, 6, right? So now I'll be sitting here like this. Then I'll do my merge step. We'll have our copy of the list. So this will be 1, 3, 4, 5, 6, 7. We'll copy that stuff back over here. Now our second call to merge sort ended. We did our final merge step, and our list is now sorted. Does that make sense? All right. So for class on Wednesday, implement merge sort. You will not like this assignment. I would highly encourage you to work with a group or something like that. Go back and watch this video. You've seen that this wasn't that hard to go through by hand. What you're not going to like is those calls to merge sort. And especially having 2 recursive calls is going to make you feel uncomfortable. This assignment is supposed to make you feel uncomfortable. But trust me when I say it's not that hard. Okay? But you're going to feel uncomfortable when you're writing it.
You call it, right? You just,
Oh, 1 second. If you haven't already done so, you have one last chance. Sign up for the hackathon by contacting Professor Josh Lockley. We're putting together teams today. So we'll be contacting the team so they can start communicating with each other about the projects they're going to be working on. Also, tonight at 5 p.m. in this room is the Grace meeting where they're going to be talking about the hackathon. So I encourage all of you to come to that and talk about ideas for the hackathon. There's a chance to win prizes. Huh? 5 p.m. is the Grace meeting tonight. Tomorrow night's the boot camp for 6 p.m. Yep. Grace meetings in here at 5 p.m. tonight. Come and help brainstorm hackathon ideas. There'll be food.
oh,
All right, go ahead.
so you're gonna define merge sort, and within merge sort, you're gonna like do. That's how I don't even know that.
I'll define a function called merge sort,
Right.
and within merge sort, I'll call merge sort and merge sort.
Okay.
You know, there'll be 2 calls to merge sort within the function called merge sort.
Okay. All right.
But they will only get called when I don't deal with a 1 list. If begin and end are the same, so merge sort itself will take in 3 parameters. It's going to take in the list we're sorting, we'll take in the beginning of that list, and it'll take in the ending of that list, the positions. Okay? So we're passing the same list around, but with a different begin and end each time through. Does that make sense?
Yeah, that sounds fun.
Okay. It's not hard, but you won't like it.
All right.
Right?